Far out.
So weird. It's kind of delightfully weird.
It really is.
So this is a five-legged robot. I have kind of a history with five-legged robots because I make hands, like mechanical hands.
Right.
And I think about Stalker as a successor to some extent to Axis, which is the five-legged robot hand that holds the BattleBots trophy.
Yeah.
So Stalker is a robot that I made about 3 years ago. It had its debut at Robo Games, and then I did a presentation of it at BattleBots. And it is a personal project that exists as an excuse for me to learn some math. So here we go.
Oh. No! I was literally wondering, I wonder if I can jump on top of it. I'll bet I can.
Well, the answer is yes. So Stalker, wow. Let's go through some of my progressions here. So this is like a real departure from everything that I normally do. It is I gotta turn my filtering way up. So this is where I can get rid of some of the jitters. It's much more of a robot than a puppet. So right. it will do some of the things that I tell it to do, but I'm just making suggestions. I'm suggesting that it walks over there, or I'm suggesting that it walks over here.
And you're giving it parameters like body height and direction, and that's it.
Right. But like, you know, the walking gait, but it has a lot of personality.
It really does.
In a strange way. It's like, actually, it creates a face. Like, it has no face. It's completely radially symmetrical.
Yeah.
But then, as it's moving around, it starts to seem to have intention.
Wow.
So the inverse kinematics is the thing that I wanted to learn, right? And this is something that I've seen other robots do for decades, like literally decades. You'll notice that the feet are on the ground, and the body is changing its orientation.
Yes.
So it's like a motion base.
Right, like a Stewart platform or something.
A Stewart platform, except that it has each leg has to cooperatively move the body around in this way. So
it takes movement from all of them in different degrees.
Right. But then I can also do things like bring the body up, and now the tip of that leg is actually remaining stably in space.
Like a chicken head.
Yeah. So even if I move the body around, right? That is inverse kinematics, right?
Ah, okay.
That's inverse kinematics. So, and then I can, you know, turn this into a...
What? No. Oh, no way. Shades of Dr. Octopus a little bit.
A little bit.
Wow. When you say you wanted to use this to learn math, what specifically about, what do you mean?
So there's linear algebra, rotation matrices, matrix multiplication. It is a whole class of math that enables things like a Stewart platform to really compellingly move something in space and move it in a way that I have not previously been able to do with accuracy. I fake it. Most of the time I just fake it.
Right.
Right? Because I'm making stuff move. I'm making stuff move in, I'm switching between presets to make it do this.
Yeah.
So, like this thing that it's doing right now, it almost looks like a person like perched on their hands and legs, like moving around. That, how would I do that as a puppeteer? How could I possibly do that?
It's so many axes of movement work to such extremes.
Right. So it's the thing we talk about. It's like, well, do you have like one person who's controlling the body and then a different person controlling each leg? It's like, no. I want to give the robot all of the agency that it needs to do all of that on its own.
Right.
So at that point, it is much more truly a robot.
Can it stand up on two legs and?
Not yet. This is kind of
A test platform?
It's a test platform. I'm going to get as far as I can with this. I think that I'm going to, I'm going to make Stalker the best 5-legged walking robot that I can make.
Yeah.
And then I'm going to move on to what I'm already calling Night Stalker, which is the successor to Stalker.
Can I stand on it?
Yes, stand by.
Okay.
Now, nobody gets to stand on Stalker, but I'm going to let you stand on Stalker. So, and if I tell you to get off, jump.
Copy. Oh my God, it feels so solid.
Yeah, it's like a table, right?
Yeah.
It's like, yeah. You'll know if it has trouble holding you
right.
up. And it won't. I think it should be fine. You'll also notice that it's totally silent and completely rock solid.
It really is. Yeah,
So-
like, it feels like basically I'm standing on a welded table.
Okay, time to get down.
Okay.
So among the things that it does not do, it doesn't have a sense of touch.
Right.
Right?
Right,
It doesn't,
okay.
it has some sense of proprioception, but I want it to be able to have like a knowledge of, is its top level to the ground or to gravity or not? So
Right.
if it's walking on rough terrain, can it manage that? If it wants to walk upstairs, can it manage that? So what do I have to learn to make it do those things? What do I have to do to make it even more independent than it already is? And that's the kind of the journey that I'm on with the development of this robot.
I love this. Is the second Stalker going to be larger or smaller?
Well, it's going to be about the same weight. I think the body will be a little more compact.
Yeah.
So one of the things that I think is very interesting about a 5-legged robot in particular is that, is it a hexapod that's missing a leg, or is it a quadruped with an extra leg?
Sure,
Right?
yeah.
So I tend to think of it as the latter. I think of it as a quadruped that has an extra leg. And one of the things that you get with 5 legs is you get all this room, like there's this big quadrant that's available, space available for this leg to move around.
Right,
The more
right.
legs you have, the narrower those spaces are. So in a way, when I think about, if I go up to another one of these poses, let's say this one. So now it's a quadruped, right?
yeah,
And
clearly.
you could imagine that if I had like maybe one more degree of freedom here, or if this whole thing was just a little more compact, now you can imagine it like walking through a door.
100%.
Like a standard
That's
door.
why I was wondering about the size, because I was thinking about this walking up and downstairs or walking through a house.
So the proportions are going to change.
Right.
I would say the overall stature is going to be the same, but the the body will be more compact, and the legs will be about the same. I think. I feel like this, size-wise, it feels about right to me.
And every joint's being driven by 2 servos.
Currently, only the base joints are being driven by 2 servos.
Oh.
Well, actually, let's rephrase that. So, this is the joint stack. So I have 2 servos here driving pitch, which is the up and down axis of this joint.
Right.
And the reason why there's 2 there is because this is the root, the one that has the most mechanical disadvantage.
Yeah.
Then the next joint, so we stack. We have pitch followed by a yaw. So this is side to side, followed by another pitch here. If you compare that to axis, for example, it's like it's a much simpler. There's like roll followed by 2 pitch axes, and that can be described by just a triangle that rolls around. This is not an easy kinematic chain to model.
Fascinating.
I got the assistance of an Imagineer on that, which is very helpful.
When you're doing this math, you're using a computer to also help you with the math. Is that right?
Yeah.
I mean,
Right,
But
so-
even still, it's non-trivial to come to results that are useful to you.
I was flying back from a vacation. I had like 10 solid hours on a plane.
Yeah.
And I basically took a gummy and coded for 10 hours straight.
Fair.
And when I landed, it's like, okay, I got it, right?
Amazing.
And the epiphany was that I had the relationship, the kinematic relationship was backwards. So much like Chuck Norris, Stalker does not do push-ups. Stalker pushes the earth down. Right. So I had to think about it like that. Stalker is not walking on the earth. Stalker is moving the earth under Stalker. So in that case, that solved the mental roadblock that I was encountering.
Fascinating.
But basically, it's a it's a frame in relation to a frame in relation to a frame. So the frame is the earth. And then there's this other frame, which is the body of Stalker. And that moves around. So you have this thing called a rotation matrix. And you can translate it up and down and around in three-dimensional space. And you can rotate it around in three-dimensional space. And then you have the legs. And they all have their own frames.
Yeah.
And then like the end of the leg. And how does that? And then there's this radius from the center of the ball to the tip of these little barnacles on the end. It's like, it's really fun, but it also is mind-blastingly complicated sometimes. And I'll show you what it looks like in my software. I don't write code in typical coding languages. I write code in Max, which is a node-based language. It's a very visual coding environment.
Right.
And so you wind up with these very visual representations of numeric operations. And it's actually, I think you'll like it when you see it.
I'm really fascinated by this construction too. All the plastic is 3D printed.
Yeah.
The aluminum is cut by a vendor.
So this is water jet cut aluminum.
Yep.
And 3D printed. So depending on what it is, so this is nylon 12 CF. This is nylon with a ton of carbon fiber in it, sandwiched between these two plates. This is a very efficient construction. So there's 5 of these. Then there's this part here. There's 10 of those, because I've got 2 for every leg.
Right.
Then there's this part, and there's actually 20 of those, because that part and that part are the same.
Oh, nice!
And then that part and that part are the same, right?
Yeah,
and then there's 2 of these and 1 of those. So we can actually look up here at this leg to talk this through.
Yeah.
So how many parts is that? For a leg, that's 1, 2, 3, 4, 5, 6 parts. And then
different numbers.
And then multiples of that to put the whole thing together. So it's like literally 6 files to make that. And then a handful of files for the body.
And you're sinking inserts into the nylon
Correct.
CF, and this gives, I'm assuming this gives a tremendous amount of rigidity.
It does. So here's a leg, and here's one of those things. So there's the there's the inserts you were talking about, right? So it's a very very fast way of making stuff.
And light.
And very light, right. And we talked about, okay, what are the issues with putting weight out at the end of the limb? Well, I put this motor here, right here at the knee joint. I thought about putting it here and doing like a belt drive or something like that. Right. But I thought, well, I'll just try it out here. And then it's like, I'm gonna put this heavy motor in here for the pincher. And then when I ran the robot, it's like, you can't even tell.
Right.
You can't even tell that there's extra weight down here. So sometimes it just doesn't matter.
Yeah. I mean, I would assume also if you needed extra strength out here, you could add a second servo on the other side and get double.
Just size-wise, I mean, probably not here, because that's the whole servo. If I had 2 of those, if I had 2 of those, it would look like this.
I see.
But the servos that I'm going to, maybe I could do that.
Amazing.
Right, because I'm going to be using different servos for Night Stalker. So I want Night Stalker to be much faster also.
Yeah.
The other sort of inspiration for this was around the time when I was thinking about making this, I was wrapping up on Stuntronics Spider-Man. And that robot, that's
the one that flies
through
the air.
That flies through the air, right? So it's this humanoid robot. It's got some servos in it. It weighs about 90 pounds. Or my prototype was like a 90-pound prototype, but like this super dynamic thing. I'm like, wow, a 90-pound thing. Well, if I made a 500-pound robot and every leg was like one of those, like had that amount of dynamics, right? It's like, that could be pretty great. So I sort of scaled down the idea and just said, I'm just gonna make a nice dynamic leg and then attach them onto an empty box, right? So, because that's pretty much what the body is.
It's mostly an empty box.
It's mostly an empty box. And I could even put the batteries, for a while I was thinking about putting the batteries inside
each leg.
That there, but it works out nicely to have them here. The other thing, just in the limitations of my ability to code, there is a microcontroller in here that's doing some of the work, coded by my dear friend Tim Lamb, who's a genius. But a future version of this would probably have like an actual computer in there, like there's some great small computers now. That you could put in there.
They're getting smaller.
They're getting smaller and smaller, yeah. So I could have like a powerful internal computer. And the reason why I would want to do that is to have that very high speed loop going to all these servos and not having to do any wireless. Where whatever's wireless is like very high level commands, like go over there, and the robot has got this incredibly complex, incredibly fast communication loop going on locally within it.
Oh man, I'm suddenly visualizing the whole middle being gone.
Right. Well, I have the prototype, the carcass of which is elsewhere. It's a donut. There's a hole in the center of it. But
you can put a tourbillon in there.
Yes, or a turbo.
Yeah. Oh man, it is so beautiful. I love this is how you're challenging yourself.
Thank you. Want to drive it?
Yes, I want to drive it.
It's kind of horrible. I'm gonna turn the sensitivity of the stick down a little bit. So see that's 100%. I'm gonna turn this down to like 50%.
Okay. These are representing the two joysticks.
Yes. So this one, let's take it down to its low position. So when you command it, here's kind of what's going on. It's like from a high level. Here's how the control system works. Yeah. If I tell it to translate its body around, then it will do that. And all 5 legs will cooperatively make that happen.
Right.
So this little stick on the right here, this is my X and Y. Then I've also got this pitch and roll here. And then I've also got up and down.
Right.
If I do something that causes the circle described by the legs to change diameter, it will pick up its feet and step to that new size. So I'm going to change its height, and by necessity, its legs are going to have to come in
order to get to
that position.
Amazing. So and it's making that call on its own.
It's making that call on its own, right? So let's go back to low walking and have at it. This is throttle and steering, and you'll find that you can, if you twist it, you'll find that you can make it turn on place, and you can also. You see that little black marking there? That's basically,
yeah.
That's basically towards you. So if you pull the stick towards you.
Oh, I see.
Right?
That's describing.
Yes, perfect. So you're walking towards me now, exactly.
Right. And it's just taking the input of direction and it's making all of its own calls.
Right. So you have the option of either just like driving it around in this XY where its orientation doesn't change, or you can steer it too if you decide that you want to have like the claw leg end up in a particular spot.
Well, what I noticed when I settled it is that it did a little extra reset. So is it making compromises for its position based on what you're asking it to do, and then when it's resting, it's going back to its protocol or something?
I would say the walking gait on this thing kind of blows. And it's the thing that I'm going to rewrite first. And I'll show you why.
Yeah.
So let's see if I can get, now let's close that. How about this? Nope, not that. There we go. All right, so this is, let's go to mid-height walking. This is a representation of the feet. So these light dots are the feet in contact with the ground. And as I start to make it turn, you can see the feet come off the ground, and that triangle indicates the stability or lack thereof triangle that it's forming as the feet are in contact with the ground. Now, there's this round robin going, right? So it's basically saying, whose turn is it to take a step? And it kind of turns around. It's like, okay, right now, well, it's your turn to take a step.
Oh,
but as I crank this, you can see, let's say if I turn in this direction, as I increase the amplitude, I've got this nice, kind of stable-looking triangle.
Yeah.
Right? Looks pretty good. If I crank it in this direction, the triangle gets very narrow and unstable. So it has a preferential kind of handedness where it works better if it's turning in one direction than the other.
That's far
because it's not acting like a hexapod or even a pentapod. It's the
turn taking.
It's basically it is a gross oversimplification of what it should be doing.
Right.
Which is what I did to really get it done.
Gotcha.
And now that I know what not to do, I'm going to do something else. And I've drawn many different iterations of a walking gait, but yeah, see, it's way better if I do it like this. So, and then even walking linearly, it's actually better if I'm like turning slightly to the left, right? It's kind of cool looking, but then like it kind of falls over, you know?
Yeah.
So.
Wow. Man, incredible.
So when I took this to BattleBots, I was in the pits, and Luke Conley came over to me. This was like 3 or 4 years ago. And he said, yeah, Leo was asking if this was Rocky. I'm like, Rocky, what are you talking about? Oh. So
from Hail Mary.
Yeah, so anyway, needless to say, I read the book, and then I tried to get in contact with those guys, with the, you know, Lord and Miller, to see if they wanted, if I could get this in the movie.
Yeah.
But it was, I never heard back from them, so.
There's, what I find really surprising about it is, as just a platform for exploration and learning for you, its simplicity has a commensurate beauty that is shocking to me.
It looks very much to me like a sand dollar.
Yeah.
The back of it especially. I think there's something just
some
kind of
echidna going on there.
Just like very inherently beautiful, this kind of pentagonal shape.
Yeah.
I'm always inspired by nature, and there's a whole fascinating like crinoids and you know, 5-legged sea creatures that don't really make any sense to us on land, but in the undersea world.
Now I just thought of a movement where it goes and just ends up doing full cartwheels.
Yeah, yeah.
Which doesn't seem totally impossible.
It does not seem totally impossible. Well, it's not only radially symmetrical, it's also symmetrical top to bottom.
Oh, that's great.
It can completely.
So it has no preference.
It has no preference, right? It can completely invert, and that's just a.
Listen, until this morning, Tars was my favorite robot ever.
Thank you. That's awesome. I'm a fan of Tars too. I think it's a little dogmatic, but
yeah,
but I do love the idea.
I just loved how what a unique approach it was, embedded so centrally.
Yeah.
A new idea. Oh my God. And so presumably, touch and proprioceptive abilities only increase what is possible.
Yes.
But you're looking to solve a lot before you even get to any of that.
Well, the first thing that I want to solve is just give it a sense of force feedback.
Right.
Which I can do a little bit of that with this if I put a computer on board, because I can read the, like, how hard is every servo working?
Right.
Does it know what direction gravity is pulling in? I can add that to this version of the robot.
Right.
Where it really gets interesting is where the motors actually have local joint force sensing. And then what do I do about its impression of its contact with the ground?
Right.
So these little nubs that you see on the ends of the legs, I mean, that is it was kind of a quick solution to the problem of, well, I want to put like a rubber ball on there. Yeah. And I basically just screwed these little rubber feet onto the tips of the legs.
Oh, that's all that is.
Yeah. So each one of these is, this one's loose, I'm going to pull it out.
They're replaceable.
They're replaceable, yeah, because they do get worn down.
Yeah, I did.
So there's a...
Boston Dynamics said that the feet were one of the most difficult engineering problems of that bot.
Yeah.
Of Spot.
I can absolutely believe it.
Yeah.
So there you go.
And they turned out to feel really lucky that it just happened to have their office near a sneaker company.
Right.
That's so cool. That's really.
Right.
Dude.
So then, like, okay, do I talk to like Keith McMillan and like come up with some kind of force sensing version of these?
Right.
So that not only do I get force sensing locally, but then I can also sort of say, oh, number 25 has a lot of force against it. That means that the force is coming from X direction.
Right.
You know.
Wow.
I mean, that's maybe that'll work. So,
And presumably all 5 legs could have this, and then it doesn't matter which direction it's going in.
I have said before, I always like to have a surprise.
Yeah.
So I want every leg to have a surprise.
Not just like a different surprise.
A different surprise. Every leg would have a different surprise.
Oh, wow.
And a clue to what those surprises might be is one of the poses that it goes into. So if I get out of this and go into this other surprise, what we're doing now is bimanual teleoperation. So each one of these legs would then have a deployable additional
different kind
little,
of grabber.
Little grabber, a manipulator thing.
Oh my
so
God.
here you can hold that, and then this is a metal version here. So these basically live inside this, and I know that I should add another degree of freedom here at the upper arm. And once I've done that, then these things can reorient, and now you have basically like a surgical robot that pops out of this robot. So, and again, this sort of like teleoperated bimanual thing is something I've done before, and it's like totally in my wheelhouse. It's like, oh yeah, I absolutely want to do this. And then the question is, where do the cameras go? You know, and then I've got 2 more legs, and I can put other weird things in them too. So it's a little bit like an indexable tool kit. So think about it. Yeah. It walks up to a, let's get it out of this mode here. Take a step back. So it walks up to a space, and it's like, okay, I'm at a door. Well, I'm going to use this leg to, no, not that leg. Let's index around. So it reindexes itself, and brings the correct leg up, and now that's the front. Right? Because the front is whatever you want it to be. So, and the front could be, this leg could be the front, or these 2 legs could be the front.
Right.
That's how granular you can make it.
Wow. Well, so we haven't even talked about him resting on his knees.
We have not talked about that. Yeah, interesting, because it could totally do that. I'm imagining, like, if you put a rubber surface on this, and then you actually flip it up, and it comes down and rests on its elbows like that. So as opposed to bringing them in. So yes, it could flip them up, but it could rest on its knees. Interesting idea. Yeah, because it can basically just like place itself on the ground. The possibilities are endless.
Dude, that is
It's a playground. It's a playground that is expensive and time-consuming.
You've helped me articulate something I've always admired about you, which is the fact that when you are solving problems, there's a simplicity to your execution that has an aesthetic purity I find remarkable.
Thank you.
This is just so lovely, and its loveliness is based in its simplicity. For me.
I try. Thank you for noticing.
Oh, man.
Thanks for noticing, Adam.
You're welcome. Oh my gosh.
So, yeah, I don't know when Night Stalker is going to make its debut, and I don't know when I'm going to get around to putting all the force sensing and gravity sensing and what have you. But it's definitely a priority.
Oh man.
Thank you guys so much for watching that video. I would be remiss if I didn't tell you we have some excellent merch. We have a 5-pack of demerit badges for sale right now at tested/store.com. We've got the I hung it off of level demerit badge, the I built the chair backwards demerit badge, the I hit my thumb with a hammer demerit badge. We've got the stapler in my finger demerit badge, and my favorite, I stuck the duct tape to itself demerit badge. Get yours now, tested/store.store. Tested-store. Tested. It's right here. There. Just click there.